Digital circuits can be categorized into combinational logic circuit and sequential logic circuit. In combinational logic circuit, the output is a function of the present inputs only. On the other hand, in sequential logic circuit, aside from the present inputs, the output also considers the past states of the circuit as well. And these past states depends on the previous inputs. Therefore, the sequential logic circuit must have some memory block that can store the previous status of the output or previous status of the input or previous status of the circuit in general. In a way, there is a feedback mechanism for this kind of circuit. There are devices that can store a binary state as long as they have electrical power, and hence they can serve as memory elements. The internal structure of these devices also have an internal feedback so that they can switch from voltage high to voltage low and vice versa. These devices are called latch and flip-flops. The subtle difference between a latch, not shown in this diagram, and flip-flop is that a latch is level triggered and a flip-flop is edge triggered. But for practical purposes, we will just focus on flip-flops and even consider flip-flop versions of some latches. For example, if we have an SR latch, we will just explore its flip-flop version, which is the direct coupled RS flip-flop, etc. In our class, we will focus on these four flip-flops. The first one is the set-reset flip-flop or the SR flip-flop. It has an input for set signal, an input for clock, and an input for reset signal. SR flip-flop has an output symbolized by Q and an inverted output symbolized by Q prime or Q bar. Next is the data flip-flop or the D flip-flop. It has an input for the data and it has an input for the clock. It has output symbolized by Q and an inverted output symbolized by Q prime or Q bar. Next, we have this JK flip-flop. It has an input for J signal, an input for clock signal, an input for K signal, and it has an output symbolized by Q and also has an inverted output symbolized by Q prime or Q bar. Finally, we have the toggle flip-flop or the T flip-flop. It has an input for the toggle signal, an input for the clock. It has an output symbolized by Q and an inverted output symbolized by Q prime or Q bar. Let's look at one sample implementation of SR flip-flop using an AND gate and NOR gate. Since we have an AND gate and NOR gate, let me write down the truth table for an AND gate. This is our AND gate. It has inputs A and B and its output is X. So if this is input A and this is input B and this is output X, the possible combinations of inputs A and B are 0, 0, 1, 1, 0, 1, 0, 1. For an AND gate, the output will only be 1 if both A and B are 1 and the rest will be 0. Next, since we have a NOR gate, let me write down the truth table for a NOR gate. For example, if this NOR gate has an inputs of C and D and an output of Y. So if this is input C, input D, and this is the column for input Y, the possible combination of inputs C and D are 0, 0, 1, 1, and 0, 1, 0, 1. So if this is an ordinary OR gate, this will be 0, 1, 1, 1. But since this is a NOR gate, we will reverse this or complement this. So we will have 1, 0, 0, 0. So going back to this implementation of an RS or SR flip-flop, when analyzing this kind of circuit wherein you have a feedback coming from the output, let's assume that at the beginning, the outputs both are set to logic 0, meaning to say it doesn't have any voltage supply. Let's try to see the outputs if we supply the set signal with 1 and the reset signal with logic 0. During this instance, we supply this clock signal with a clock pulse, a positive edge. So essentially, these two inputs here are in logic 1. So looking at this AND gate, 1 and 0 will produce, based on this, will produce an output of 0. And since this is 0 and 0 will produce an output of 1. Let's look at this AND gate. The inputs are both 1, so this will produce an output of 1. And since this is 1, based on our truth table, we have an output of 0. So when we supply set with logic 1 and the reset signal with logic 0, its output becomes 1 and its inverted output is 0. In other words, when set is 1 and reset is 0, Q is set to 1. What if this time we both supply set signal and reset signal with logic 1? And of course, during this instance, the clock gives a signal. So essentially, these inputs here are in logic 1. So this first NAND gate will have an output of logic 1. And since this is initially 0, 0 and 1 will produce an output of 0. And looking at this AND gate, this will produce an output of 1. And since this is 0, this will produce an output of 0. Note that the output is 0, but its inverted output is also 0, which violates our condition that Q bar must be the inverted output. Meaning to say, whatever the value of Q is must be inverted, and that would be the value of Q bar. When we supply the set signal of an RS flip-flop with 1 and the reset signal with 1, this is an invalid input because the output of Q and Q bar are contradicting. Hence, the inputs 1 and 1 for S and R are actually indeterminate inputs. Indeterminate. And this is one of the disadvantage of an SR flip-flop. We don't have a way of preventing this invalid inputs. For the third case, what if we supply the set signal with logic 0 and the reset signal with logic 1? Again, during this instance, we sent a clock pulse. So essentially, these inputs here are both logic 1. So for this first AND gate, its output would be logic 1 and this is 0. And the output of this NOR gate will be 0. Next, for this AND gate, its inputs are 1 and 0, hence its output will be 0. And since this is 0, the output of NOR gate will be 1. When the set signal is 0 and the reset signal is 1, Q or the output will be set to 0 and its inverted output will be 1. Hence, when set is 0 and reset is 1, Q is set to 0. What if we supply set and reset again with a simultaneous 1? Let's see what will happen. So I'm going to write a logic 1 for set and logic 1 for reset again. Let's see if this will still result to an invalid output. So again, we will be supplying a clock pulse. So essentially, these inputs here are both in logic 1. So 1 and 1 for this first AND gate will result to an output of 1. And since this is 1, 1 and 1 for this NOR gate will result to an output of 0. Next, for this second AND gate, its inputs are both 1 and 1, hence this will result to an output of 1, and since this is 0, the output of this NOR gate will be 0 as well. And recall that the output and the inverted output are the same, hence this is an invalid set of outputs. Therefore, we established the fact that when set signal is logic 1 and reset signal is logic 1, this results to an invalid output. Hence, these inputs are invalid and result to an indeterminate state. For the final case, we will retain these previous values of outputs where Q is 0 and Q bar is 1. What if we supply the set signal and reset signal with a simultaneous value of logic 0? And at this instance, there is a clock pulse, which means that these inputs are both in logic 1. So for this first AND gate, this will result to an output of 0. And since this is 1, for this NOR gate, the output would be 0. Next, for this AND gate, since the inputs are 1 and 0, this will result to an output of 0. And since this is 0, the output will be 1. So for the case where set is 0 and reset is 0, the output of Q and Q bar remains the same. So when both set signal and reset signal are in logic 0, then there are no changes in the values of Q and Q bar. Let's now fill up this SR flip-flop excitation table. Excitation table is important when you are constructing sequential logic circuits using flip-flops. Excitation table shows the changes in the value of the output, or specifically Q, after one clock pulse. And it also depends, or it's also a function of the current or the present inputs of the specific flip-flop. The possible combinations of QT and Q of t plus 1, meaning to say the new value of Q after one clock pulse, are the following: 0, 0, 1, 1, 0, 1, 0, 1. So let's look at the first case where initially the value of Q is 0, then after one clock pulse, it is still 0. So based on this table, if we will look at the cases where Q is 0, there are two cases. One is where SNR are 0, 1 and SNR are 0, 0. Hence, Q remains 0 when the set signal is at logic 0 and the reset signal based on these instances is either logic 0 or logic 1. Hence, I'll just put a don't care here. Next, let's look at the second case where initially the output Q is 0 and then after one clock pulse, it becomes a 1. This is only possible when set is logic 1 and reset signal is at logic 0. So I'll put 1, 0 here. For the third case where initially the output Q is logic 1 and then after one clock pulse, it is now at logic 0. So looking at this table, this is only possible when set is at logic 0 and reset signal is at logic 1. Note that I'm not considering the indeterminate state. Finally, we have this fourth case wherein initially the output is at logic 1, then after one clock pulse, it remains at logic 1. Based on this setup, I'm going to write 1, 0 here, but this is also possible wherein the output of Q do not change when both set and reset are equal to 0. Remember that when set and reset are both equal to 0, it doesn't change the output Q. Hence, this is also possible for the case where set is 0 and reset is 0. Therefore, this final case of excitation table is also possible for 0, 0. So instead of writing 1 for the set signal, I'm going to write don't care here to include this possibility where set and reset are both equal to 0. And that's it. This is our SR flip-flop excitation table. Let's now explore the behavior of a D flip-flop or a data flip-flop. To explore its behavior, let's consider this one example of implementation of D flip-flop, where D flip-flop is constructed using NAND gates and one NOT gate. Since this circuit uses NAND gate, let me write down the truth table for a NAND gate. This is just an AND gate with a bubble in front of it to negate its output. If my inputs are designated with A and B and its output is designated with Y, then we have the following truth table. This is my column for input A, column for input B, and column for output Y. The possible combinations of A and B are 0, 0, 1, 1, 0, 1, 0, 1. For the output, this is just the truth table for AND gate, but its result is complemented. Hence, the output would be 1, 1, 1, 0. So in filling up this table, let's assume that initially the output Q has no voltage, meaning to say it is at logic 0. There will be two cases for this one. Either we supply the data signal with logic 0 or logic 1. Also, we can assume that initially the output Q is at logic 1 and we can supply this data signal with either logic 0 or logic 1. So to write down the possible combinations of this flip-flop, we will fill up this table. So the possible combination between D and Q are the following: 0, 0, 1, 1, 0, 1, 0, 1. So for this first case, we assume that the initial value of the output Q is logic 0, and we try to supply the data signal with 0. So let's see what will happen. This input here is directly connected to D. This would be 0. However, since this line passes through a NOT gate, the input here will be 1. And at this instance, we assume that there is a clock pulse, a positive edge clock pulse. Hence, these two inputs here are both in logic 1. For this NAND gate, since the inputs are 0 and 1, this will result to an output of 1. And since this Q here is at 0, its inverted output must be initially at 1. The input here is actually also 1. So 1 and 1 will result to an output of 0. So I will retain this value here. Next, let's look at this NAND gate. 1 and 1 will result to an output of 0, and since there is a 0 here, this will result to an output of 1. In other words, the value of Q is retained. So let me write next clock pulse Q here. There's no changes in the value of Q here. There's no change. Next, for the combination where initially Q is at 0 while we will supply the data signal with logic 1. Therefore, this will be logic 1 and this input here will be logic 0. Then again, we have a clock pulse here. So this is logic 1, logic 1. So for this first NAND gate, this will have an output of 0. And since this is 1, this will result to an output of, this Q here will become 1. And for this NAND gate, the output would be 1. And since this is 1, the output will be 0. So I'm going to write 0 for this Q prime here. Notice that when we supply the data signal with 1, the value of Q changes to 1. Hence, this sets Q to 1. By the way, the new value of Q here after one clock pulse is 1. Consider this third case wherein the initial value of the output Q is 1 and we supply the data signal with logic 0. Since this is 0, this will be 0, and since this is connected to a NOT gate, this will be 1. Again, during this instance, we sent a clock pulse to enable these signals to pass through these gates. This would mean that these inputs are both in logic 1. So let's begin with this gate since we already have a value for this one. Since both inputs are 1, this will result to an output of 0 and this is 1. 0 and 1 for this NAND gate will result to an output of 1. And for this NAND gate, we have 0 and 1. This will result to an output of 1. And since this is 1, 1 and 1 will result to an output of 0. So the new output of Q after one clock pulse is 0. Let me write it here. And the value of Q bar or the inverted output is 1. So it seems that for this case, where initially the value of Q is 1 but you supply the data signal with logic 0, it changes the value of Q to 0. Hence, for this case, this resets the value of Q to 0. Now for the final case, the initial value of Q is 1 and we supply the data signal with logic 1. Hence, this is 1, and this passes through a NOT gate, so this becomes 0. At this moment, we supply it with a clock pulse, a positive edge clock pulse. And this would mean that these inputs are both in logic 1. So let's begin at this NAND gate since we already have an input coming from this Q. 1 and 0 for this NAND gate will result to an output of 1, and since this is 1, 1 and 1 will result to an output of 0. Next, for this NAND gate, 1 and 1 will result to an output of 0, and since this is 0, 0 and 0 will result to an output of 1. So the new value of Q after one clock pulse is still 1, and Q bar is 0. So it seems that for this final case, there is no change in the value of the output Q. So the possible combinations of Q of t and Q of t plus 1 are 0, 0, 1, 1, and 0, 1, 0, 1. This column here is the initial value of the output Q. Then after one clock pulse, it will now have a new value which is designated by Q of t plus 1. So for this first case, 0, 0, based on this table, 0, 0, this is possible when you supply a data signal of logic 0. Next, for this second case where the initial value of Q becomes 1, this is possible for the second case, wherein you supply D with logic 1. Next, for the second case where initially Q is 1, then after one clock pulse, it becomes a 0. This is similar to this third case. And this is possible when you supply the data signal with 0. And finally, you have this case wherein initially your output is logic 1, but after one clock pulse it didn't change and it's still 1, and this is similar to this case wherein you supply the data signal with a value of logic 1. So this is our excitation table for D flip-flop. Let's now explore the most versatile flip-flop, which is the JK flip-flop. The name JK flip-flop comes from its inventor, Jack Kilby. So the J input in a JK flip-flop is similar to the set input of an SR flip-flop, and the K input of a JK flip-flop is similar to the reset input of an RS flip-flop or an SR flip-flop. So the possible combinations of J and K are the following: 0, 0, 1, 1, 0, 1, 0, 1. In order to explore the behavior of a JK flip-flop, we will be using this one example of JK flip-flop where it is constructed using a bunch of NAND gates. Here we have 3 input NAND gates and 2 input NAND gates. So just to guide us, if you have 2 input NAND gate, if both of its inputs are in logic 1, then this is the only time that this will result to an output of 0. Otherwise, this will be equal to 1. Next, if we have 3 input NAND gates, if all of these inputs are in logic 1, then this is the only time where this will result to an output of logic 0. So otherwise, this will result to an output of logic 1. So for the first case, 0, 0, let's just assume that for now, the output Q has 0 voltage, or meaning to say it is in logic 0. So I'll put 0 here. And we supply this J with, for first case, JK will be supplied with both logic 0. During this instance, we send a positive edge clock pulse, which means that these inputs here are both in logic 1. Since we already have a 0 here, the output here will be 1. So let's examine this NAND gate here because we already have an input for this wire here, and it's 0. 0 and 1 will result to 1, and for this input, since this is 1, 1 and 1 will result to an output of 0. So I'll put, for Q bar, I'm going to put this value here. After one clock pulse, let me just put it here, Q of t plus 1. After one clock pulse, the value of Q is still the same, 0. For this case, where J and K are both 0, there is no change in state of the output Q. Next, what if we supply J with logic 0 and K with logic 1. Since we already have a 0 input here, we are assured that its output will be 1. By the way, we have a clock pulse here. We supply this with a positive edge clock pulse, which means that these inputs are both in logic 1. And initially, since we assume that Q is 0 and its complement is 1, this 0 here will propagate along this wire. And hence, we also have a 0 here. Therefore, the output of this NAND gate will be 1. So let's examine this first, this NAND gate here. This is 0, 1, and this will result to a value of 1. And for this NAND gate, we have 1 here, and we satisfy this condition. Hence, this will result to an output of 0. So for this instance, the value of Q is 0, and the value of Q bar is 1. The value of Q is still 0, so I'm going to put 0 under this value of Q after 1 clock pulse. To describe this state, I can put no change because the value of Q was not changed during this process. But if you try to assume that the initial value of Q is 1 and then apply logic 0 to J and logic 1 to K, then this will result to a value of 0 for the output Q and a value of 1 for the complement Q. So you can try it on your own. And what this combination essentially do is that it resets the value of Q to 0. Let's consider this third case where we supply signal J with logic 1 and signal K with logic 0. And let's also assume that the initial value of the output Q is 0. Since we all have a value of 0 here, this NAND gate will surely have an output of 1. And for this NAND gate, since this is 0, this inverted output Q here, or Q bar, will have a value of logic 1. And we have a clock pulse here, a positive edge clock pulse. Therefore, these two inputs here are both in logic 1. Since this is 1, this is 1 as well. And since all these inputs are 1 based on this condition, this will result to an output of 0. So we can now begin analyzing the situation. First, how about let's try to examine this NAND gate. Here we have an input of 1. 0 and 1 will result to an output of 1. And here we have 1. 1 and 1 will result to an output of 0. So the new output of Q is now 1. And I'm going to write these outputs here. So what this combination essentially do is that it sets the value of Q to 1. So finally, we have this combination where we supply the J signal with logic 1 and the K signal with logic 1. So from previous case, Q is 1 and Q bar is 0, but it doesn't really matter. We can also assume that Q is initially 0 and so on, but this is all right. So next, we supply signal J with logic 1 and signal K with logic 1. Let's see what will happen. During this instance, we send a positive edge clock pulse. Hence, these inputs here are both 1 and the input here is actually 0. Hence, this will result to an output of 1. Next, we have a value of 1 here. Hence, all of the inputs of these NAND gates are logic 1. And this will result to an output of 0. We have a value of logic 1 here, which will pass through this wire. Hence, this is 1 and 0. And this will result to an output of 1. And this value of 1 will be transmitted to this input. And for this NAND gate, we will have inputs 1 and 1. And this will result to a value of 0. Notice that from this set of values, it has now become 0 and 1. So the new value of Q after one clock pulse is 0. But remember that the initial value of the output Q is 1. Hence, this combination of inputs 1 and 1 for JK actually toggles the value of Q. So let me delete this column here. And let's then fill up this excitation table for JK flip-flop. Again, excitation table is important when constructing sequential logic circuit using flip-flops. The value of Q here is the value of the output Q at an initial time, and then after one clock pulse, it has now a value of Q of t plus 1. The possible combinations of these two columns are 0, 0, 1, 1, 0, 1, 0, 1. So for this first case where the value of Q didn't change or it was set to 0 is given by this instance wherein there is no change in the value of Q. So I'm going to write 0, 0 here. Or this can also be a result wherein we try to reset the value of Q from 0 to 0. This is possible when J is 0 and K is 1. J is equal to 0 or K is also equal to 1. So this is actually a don't care. So again, this first case here in the excitation table is possible when J is equal to 0 and K is a don't care, or K is equal to 0 or 1. Next, for the second case, it seems that Q is set to 1 or it has been toggled. Q is initially 0, then after one clock pulse, it has now a value of 1. This is possible when we intentionally set the value of Q to 1, which means that JK are 1 and 0. And this is also possible if we toggle the value of Q, which is given by this scenario, wherein we supply J and K with 1 and 1. J can be 1 and K can be 1. So again, this is a don't care. For the third case, where the initial value of Q is 1, then suddenly after one clock pulse, it has become 0. This is possible if we reset the value of Q to 0, which means that we supplied J with 0 and K with 1. This is also possible if we toggle the value of Q by supplying J with 1 and K with 1. So this can be 1 and K is 1. So this is actually a don't care. Finally, we have this case wherein the initial value of Q is 1 and after one clock pulse, it is still 1. So there's no change. So the possible scenario is that we supplied J and K with 0 and 0. And another is we intentionally set the value of Q to 1. Even though it's already 1, we still set it to 1. So it's possible when we supply J with 1 and K with 0 and 0. So this is actually also another don't care. So this is our excitation table for JK flip-flop. One thing to note here is that JK flip-flop solves the problem of SR flip-flop, wherein if you supply set and reset with a simultaneous 1, this will be an invalid input, but JK flip-flop, try to interpret this as a toggle command. Let's explore the behavior of T flip-flop using this example of one implementation of a toggle flip-flop using a 3-input AND gate and a 2-input NOR gate. If we have 3-input AND gate, this will only be 1 if all of its inputs are 1. Otherwise, its output will be 0. For the NOR gate, the output of NOR gate will only be equal to 1 if both of its inputs are 0. Otherwise, this NOR gate will have an output of 0. So going back to this circuit, since we only have one input and that would be the toggle signal, we can assume different initial values for Q. For example, we can assume that initially the output Q is at logic 0 and we supply this toggle signal with either 0 or 1. Or we can assume that initially Q is 1, and we can supply this toggle signal with 0 or 1, and so on. To exhaust all of this combination, let's write down the combinations of T and Q on these columns, and that would be 0, 0, 1, 1, 0, 1, 0, 1. Let's consider this first case wherein the initial value of Q is 0, and we supply the toggle signal with logic 0. This will be 0. At this moment, we supply a positive edge clock pulse, which means that we are supplying these two inputs with logic 1. Since this is 0, it will transmit this logic 0 to this input of AND gate. So this is 0. And based on this condition, this will result to an output of 0. Next, since Q here is initially 0, then the complement of Q or the inverted output must be 1, and this 1 will be transmitted towards this 3-input AND gate. So this is actually 1. So based on these inputs, this will result to an output of 0. So let's examine first this NOR gate. We have a 1 here. So its inputs are actually 0 and 1. 0 and 1 will result to a value of 0. So I'm going to write 0 here. And for this one, 0 will travel here. And 0 and 0 will result to an output of 1. Let's consider the next case. The initial value of Q is 1, and we supply the toggle signal with 0. So this is 0, 0, and we have a clock pulse, a positive edge clock pulse, which means that both of these inputs are in logic 1. And this 1 here will be transmitted to this input. Since we have a value of 0 here, the output here will be 0. And without knowing the value of this line here, since we already have a 0 here, we are sure that the output of this AND gate will be 0 as well. Next, since we have a value of 1, this will be transmitted here. So the inputs for this NOR gate will be 1 and 0, and this will result to a value of 0 here. This 0 here will be the input for this NOR gate. The inputs for this NOR gate are 0 and 0, hence this will be 1. Hence, the value of this Q after 1 clock pulse is still 1. Let's consider this second case, where the initial value of Q is 0 and we supply the toggle signal with logic 1. So this will be 1, this will be 1, and at this moment we supply the clock signal with a positive edge pulse. Therefore, these two signals here are both in logic 1, and since this is 0, this will be transmitted here. Since we have at least 1 0 here, the output of this AND gate will be 0. And for this signal, notice that if this is 0, then the complement of this output must be 1. So this one will be transmitted to this input. Since all of the inputs of this AND gate are 1, then this must be 1. Since we already have a value for Q, let's transmit this value here. Hence, the output of this NOR gate will be 0, and this 0 will be transmitted here. 0 and 0 will result to an output of, based on this diagram, 1. So after 1 clock pulse, the new value of Q is now 1, and I'm going to write it here. Let us consider this final case where the current value of output Q is 1, and we supply the toggle signal with logic 1. So this is 1, and at this moment, we have a positive edge clock signal. So these inputs are in logic 1, and this value of 1 here will be supplied to this input. Hence, this is also 1. Therefore, the output of this AND gate is 1. And since we have a 0 here, the inputs of this NOR gate are 0 and 1. And this will result to an output of 0. Hence, the new value of Q after 1 clock pulse is now 0. So continuing this, initially we have 0 here. So this becomes 0. And we supply this input with 0. Hence, the value of this inverted output is now 1. So let's now fill up the excitation table for T flip-flop. So this column is the initial value of the output Q, and then after one clock pulse, it has now a new value which is designated by Q of T plus 1. So the possible combinations of these two columns are 0, 0, 1, 1, 0, 1, 0, 1. So for this first case, this happens when the toggle value is 0. For the second case, 0, 1, this happens when the toggle value is 1. For the third case, this happens when the toggle value is 1. And finally, for the fourth case, this is possible when the toggle value is 0. So this is our excitation table for T flip-flop. As a final remark, note that when the toggle signal is logic 1, the value of the output Q is reversed or toggled. On the other hand, when the value of the toggle signal is 0, the value of the output Q remains the same. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!